Okay, so we've been talking about, well, anybody have any homework questions you'd like me to go over? If you have any of those power cycle questions you'd like to see, I could do one or two of those.
Yeah, I mean, I don't think
They're pretty simple questions. You just like to see the solutions, so you know, yeah.
it's just compare, yeah.
Okay, I'll get those up.
I got through them, so.
Yeah.
Just to make sure, I think there was one question that had like, oh, one, there was one QH going into the system and then two coming out. You
Yeah.
just subtract those like twice, right? Like,
Right.
Just do them.
Just subtract them both, yeah.
Okay, that makes sense. So it's possible to have like, in that sense, like three reservoirs, I guess, because it has.
Yeah, you could have, yes,
Okay.
yes.
Yep, that makes sense.
Any other questions? Okay. Well, we've been talking about the Clausius inequality and the definition of entropy. So the Clausius inequality says if you take all of the increments of heat and divide by the temperature over the whole boundary, you get something that's less than or equal to 0. And this is for a cycle. And this has to do with an actual process. And for a reversible process, that's when you get the equal to 0. So anything that's not totally reversible, you have this integral less than 0. And then we have the definition of entropy. That says the change in entropy is equal to the integral from state 1 to state 2 of dq over t around the whole boundary. Obviously, those two are related. So think about a cycle, any cycle. And think about the change in entropy for that cycle, and think about this for the actual cycle. Okay, this one is going to be equal to, well, look at the definition of entropy. This is going to be equal to dq over t around the boundary from state 1 back to itself, because it's a cycle. That is a reversible process. So you end up, I mean, you can think about it as a reversible process that makes this an equality. Or you can think of the fact that entropy is a property, and so any property, if you go back to the starting state again, you're going to get back to the same properties. Okay, but the answer is, for that cycle, this is going to be equal to 0. And this is going to be less than 0. Okay? With me on that? And so, so for the cycle, you can write something like this. The change in entropy is equal to the integral of dq over t for the actual process plus some value sigma. This has to be positive. And it turns out you can write that for, so this is something we can just reason out from what we know, okay? And this is the start of the entropy balance, okay? And we can understand why it works like this for a cycle. You'll have to take my word for it that it turns out, it's not surprising, but it turns out that this holds between any state 1 and state 2 also. So this holds for any process, not just cycles. And so what you get is that the change in entropy is equal to the integral from state 1 to state 2 of dq over t around the boundary plus this positive value sigma. This is for the actual process. And this is positive, or 0 if it's internally reversible. And this gives us the entropy balance. That sigma is called the entropy produced. Okay, so let's come up with a system and do a calculation, see how much entropy is produced by a process. So let's say we have a gearbox. There is a rotating shaft coming out here that connects to a gear, and then that gear articulates with another gear, that comes out this way. If you measure the power of this gear, we're putting power in at 60 kilowatts. And power is coming out at this gear at 58.8 kilowatts. And we're assuming that this is steady state, so the properties inside the system are all constant. The temperature at the boundary of the box is 300 Kelvin. And we want to calculate the entropy that's produced. Well, to calculate the entropy produced, we're always going to use this equation here. And so you're always going to use some amount of heat transfer. You're always going to have to know a temperature. We see we're given the temperature here, so that should give you some confidence that you're thinking about it in the right way. So now the question is, how can we go from what's given to a heat transfer? And the first law will do that for us. Okay. So we need Q. And so we'll go to the first law. The first law says dE dt is equal to the rate of heat transfer minus the rate of work done. I'm going to think of it as what we're doing in a single second. And then we can rewrite this as the change in, we're not doing control volume stuff. You can think of this as the change in energy is equal to Q minus W. You can always do that to switch back and forth between the rate equation and the actual, finite interval of time equation. Okay, because it's steady state, this is 0. And so we have 0 is equal to Q minus this 60 kilowatts in a second, that's 60 kilojoules. That is energy coming into the system through work. So is that positive or negative work from the sign convention of the first law? Negative, yep. So in here we have negative 60 times 10 to the third joules. And this one's going out. That's positive according to the first law sign convention. So this is positive 58.8 times 10 to the third. And so Q is negative 60 times 10 to the third plus 58.8 times 10 to the third. And so the total heat transfer at the boundary is negative 1.2 times 10 to the third joules. So now we'll go to the entropy produced equation. We have that the change in entropy is equal to the integral of the heat divided by the temperature where it's transferred plus sigma. Since this is steady state, remember that steady state means all properties stay constant, and entropy is a property, so this goes away because it's steady state. So 0 is equal to negative 1.2 times 10 to the third divided by 300 plus sigma. And so sigma is equal to 4 joules per Kelvin every second. Well, if this is constant, then you can think of the rate of entropy production as being 4 watts per Kelvin. Any questions about that? Yeah.
What is the difference between every second and per second?
Well, you have to be careful that you're talking about a problem where the rate is constant, you know. In a steady state problem, the rates of all these quantities are constant. So when you have to make a switch like this, you're going to see it in steady state problems. But other than that, I mean, if all the rates are constant, then there's no difference at all. But I just sort of thought of it that way so that we could go from talking about rates per time, watts and stuff, to talking about joules, which is what our equations say. And then when I was done with that, I went back to saying like, okay, well, that's happening steadily every second. I'm just going to rewrite it in the, in like as a per second rate. If they would have said over a given interval of time, this was 60 kilojoules coming in and this was 58.8 kilojoules coming out, we wouldn't have had to think about that at all. Okay, so now what we're going to do is talk about using entropy to determine directionality in processes. So if you have an isolated system and an isolated system means this. First, no material flow across the boundary. And second, no energy flow across the boundary. Then the process moves in the direction of increasing entropy, of positive entropy, okay? By direction, I'm talking about a time direction. So it moves in the direction of positive entropy production. Like I said, you can't use the first law to determine what thing happened first and what thing happened second. And the example I gave was like a guy on a skateboard or skis and at rest at the top of a hill and with speed at the bottom of the hill. You can use energy to figure out what that speed is at the bottom of the hill, but there's no conservation of energy doesn't make any distinction between someone going fast at the bottom, using that energy to get to the top of the hill, and someone who uses the height of the hill to develop speed at the bottom of the hill. There's no way to do it. Energy can't do that, but entropy can do that. Okay, so we're going to do an example of that. Okay, so an isolated system, what would be examples of isolated systems? I think the best way to think of this is think of a rigid, insulated container. Material can't get through it. Heat can't get through the insulation. It's rigid, so there's no work. Okay. So let's do an example. Let's say we have an isolated system. With 0.5 kilograms of steel at 400 Kelvin. And 10 kilograms of water, liquid water, at 283 Kelvin. So first, we're going to calculate the equilibrium temperature of the system. And second, we're going to use the second law to show which of those is the starting state and which is the final state. Okay, so, I mean, your intuition is clear about this. You could never put a chunk of steel into water with both of them at some temperature and then have the steel get hotter and the water get colder. Okay, according to the first law, that would be perfectly fine, but it's the second law that makes that impossible. Okay, so we're going to first use energy balance to figure out the temperature, the equilibrium temperature where the steel and the water are both the same temperature. And then we're going to use the second law to figure out which one is possible and which one is impossible. Okay? All right, well, we're going to assume incompressible materials. We have a liquid and a solid. So let's think about what we know because it's incompressible. Well, we know that for each material, the specific volume is a constant. We know that the specific internal energy is just a function of temperature. Therefore, we know that the specific heats are the same thing. and they're just equal to the derivative of the specific internal energy with respect to temperature. And so we can use that to say, so from this equation here, we can use that to say du is equal to c dt. Okay, so that'll let us calculate a change in internal energy for a given change in temperature if we integrate that. And then the last thing we know is the entropy calculation that we did last time. Let's see, where do I have that written? So remember, the change in specific entropy for an incompressible material is the specific heat times the natural log of T2 over T1. Okay, so that's everything that we know about incompressible materials. So for part A, the change in, I gave masses for this, right? Yeah. Okay, so the change in specific internal energy for each one of these things is the specific heat times the change in temperature. For the steel, the solid steel, this C value is 460 joules per kilogram Kelvin. That's something you can just Google. For the liquid water, this is 4186 joules per kilogram Kelvin. The change in actual extensive internal energy is the mass of the thing times the change in the specific internal energy. And now, since this is isolated, there's no energy transfer across the boundary, we can say that the change in internal energy is equal to the change in internal energy for the water plus the change in internal energy for the steel, and that's equal to 0. Okay, so the change in internal energy for the water is the mass, 10 kilograms, times the specific heat, 4186, times the equilibrium temperature minus the starting temperature. The change in internal energy for the steel is the mass of the steel times its specific heat, 460. Times the change in temperature, so that's that same equilibrium temperature. That's what we're looking for, is when these two temperatures equal each other, minus its starting temperature. And so we get 10 times 4186 times the equilibrium temperature minus 283 plus 0.5 times 460 times T equilibrium minus 400, and this is equal to 0. now just multiply all that stuff out. It's one equation for one variable, and you get a final temperature of 283.6 Kelvin. Okay, so to us, intuitively, and this is a very intuitive case, we know that the temperatures that were given were the starting temperatures, and this is the final temperature of the whole system. But you can come up with cases that aren't that intuitive, and so we want to show how now we would calculate that this has to be the final. This can't be the starting temperature of those two things. Okay, are you with me on that? Mm-hmm. So now we're going to go to part B. The change in entropy is going to be the change in entropy for the water plus the change in entropy for the steel. That's equal to the mass of the water times the change in specific entropy plus the mass of the water plus the mass of the steel times the change in specific entropy for the steel. And we're going to use the incompressible assumption for this. So we can write this as, so first, try saying that the starting temperature is 283.6. Then the change in entropy of this system is the mass of the water times the specific heat of the water times the natural log of the final temperature. So the final temperature in this case of the water would be the one that was given. If we're assuming that it starts at the same temperature and goes backwards, the one that we know really isn't the case, but we're going to see what it shows. So the final temperature would be 283. The starting temperature would be 283.6. Plus the mass of the steel times its specific heat times the natural log of the final temperature of the steel, which we're assuming is 400 Kelvin, divided by the starting temperature. And if you punch this in, you get a change in entropy of negative 9.56 joules per Kelvin. Well, since this is an isolated system, getting a negative change in entropy is impossible. So a negative change in entropy is impossible for an isolated system. So now we're going to try the ending temperature being 283.6 Kelvin. The only thing that changes in both of those cases is what's the numerator and what's the denominator inside that natural log. which has the effect of changing the sign of the natural log. So we get that the change in entropy is the mass of the water times its specific heat times the natural log of 283.6 over 283 plus the mass of the steel times 460 times the natural log of 283.6 divided by 400. Since you changed the, you took the reciprocal of both of the things in those natural logs, you just end up with a change in entropy of positive 9.56 joules per Kelvin. This is possible. So that's the direction the direction time moves from the different temperatures to the equilibrium temperature. Any questions about that? So anytime you see a problem that asks you to determine the direction of the process, you're going to use this, you're going to use the second law, this form that makes you figure out is the total change in entropy positive or negative, okay? And if there's an ideal gas in it, you're probably going to use the ideal gas assumption. If there's a incompressible material, you're probably going to use the incompressible assumption. Yes?
So just to clarify, we will always assume that the equilibrium temperature is the final temperature.
Well,
When we're given the initial, well, not, they don't
Yeah.
say it's initial, but we give
it always will be the case. You should know that, keep that in mind. But in stuff like this, like you're going to have to do problems where you do this calculation, So just get used to how that calculation works. Okay. All right. Well, that's all I want to say today. So I have office hours from noon to 2 today, if anybody wants to talk about anything. And remember the quiz on Monday. Okay. And I'll try to remember it too.